In Italy, a catastrophic crane collapse on a major construction project.
Once this crane started to go, nothing was going to stop it.
In Massachusetts, devastation as a high-rise comes crashing down to earth.
One eyewitness said the sound was like 10 jets taking off. How could a 16-story building just crumble to the ground?
In New York State, disaster strikes a vital river crossing.
It was cataclysmic, it was sudden, and it was violent.
And in Sweden, chaos as a bridge build smashes onto a railway line.
It was shocking. All that concrete absolutely collapsed. This was a major accident.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. For engineers, protecting big structures against the elements is an ongoing battle. Overlook one detail, and the results can be catastrophic. Like this deadly bridge disaster in New York State that felt the full force of Mother Nature.
The bridge crashed more than 25 meters into the river below, taking vehicles down with it.
The devastating collapse of a crucial crossing.
A truck was found more than half a mile downstream because there was so much water moving through this channel.
This tragedy caught everyone by surprise and left local citizens reeling.
We're talking 84 to 100 feet of just steel, cement, crashing into this roiling creek below.
With more than 6.5 million kilometers of thoroughfare, the US has the largest road network in the world. And one of the nation's most important stretches is this, Interstate 90.
The I-90 is the longest highway in the entire US and stretches over 4,800 kilometers from Boston in the east all the way to Seattle in the west.
One key section of I-90 is the New York Thruway, running over 600 kilometers from the Massachusetts border to Lake Erie. Mark McGuire is a retired journalist.
The New York State Thruway is a major corridor in the Northeast for both pleasure travel and commerce. So this has been a traditional thoroughfare for America.
In a state carved up by water, the Thruway has a staggering 815 bridges, including this one. The 165-meter-long Schoharie Creek Bridge, crossing waters that flow down from the Catskill Mountains.
The Schoharie Creek, you can see it in the summer here. It is placid, it is calm. In the spring, when you have a combination of rain and snowmelt, you could turn a placid body of water like this into a raging, roiling river.
And a fast-flowing river can be very dangerous for bridges, causing a type of erosion known as scour.
Scour is one of the great challenges of river engineering. Fast-moving water can erode or scour away the soil around the base of the shallow footings, leaving the piers exposed to the elements.
But, like many bridges, here the piers are protected against scour by a layer of stone or rock called riprap.
You'll often see riprap, or rocks, placed around structures to protect not only against scour, but also wave or ice erosion.
Geotechnical engineer Peter Deming explains.
Riprap is a large stone, and usually it's a broken stone so that it interlocks and has a high friction and it joins with other rocks. The water tries to move the riprap and it can't get below the riprap because the riprap is so heavy and it's able to stay in place even with the water flowing by. The riprap is what prevents the scour from reaching deep.
The bridge standing today opened in 1988, but it wasn't the first crossing here. Its predecessor was built in 1954 to coincide with the opening of the thruway. For more than 3 decades, the first bridge served as a vital passage around 25 meters above Schoharie Creek, widely used but largely unnoticed.
Drive this thruway every day, you drive highways like this. You go over this, it doesn't even look like a bridge. You just think it's another patch of road.
The Schoharie Creek Bridge wasn't intended to be iconic or eye-catching. It was just a run-of-the-mill interstate bridge like you'll see crossing numerous waterways all over the US.
But in 1987, one devastating event etched the bridge into the minds of people across the country. April 5th, 2 days of heavy rain had caused the Schoharie Creek to swell to dangerous levels.
As a precaution, other bridge crossing the creek had been closed earlier that morning. Although the I-90 crossing was inspected, it was decided to leave this vital connection open.
A few minutes later, at approximately 10:45 a.m., disaster struck. At the time, Mark Maguire was a 23-year-old local journalist.
I first heard that there had been a bridge collapse and that the thruway was closed. And I tried to get as close to the scene as possible.
Mark was unprepared for the scale of the devastation he was racing towards.
People who witnessed the collapse, and there were more than a few, all had the same description. It sounded like an explosion.
People on the bridge downstream thought it was a bomb, and then the bridge dropped into the water in fractions of a minute.
We're talking 84 to 100 feet of just steel and cement crashing into this roiling creek below.
4 cars and 1 truck went down with the bridge. Emergency responders rushed to the scene.
State police, the sheriff's department, divers. There was even an aircraft searching the water. But in this raging torrent, it soon became clear that the likelihood of a rescue was gone.
The truck and the automobiles that came down were found in the Mohawk River more than half a mile downstream because there was so much water moving through this channel.
10 people were in the 5 vehicles that fell into the water. Tragically, none survived.
1 minute's there, next minute's not. It was a dark day.
A vital connection was now gone, lying in the creek below. And people wanted to know, how could an interstate bridge 25 meters above the water be destroyed by a swollen creek? One key suspect was the bridge's shallow foundations. Geotechnical engineer Peter Deming helped spearhead the investigation.
The investigation needed to remove the water so we could look at the foundations. So we brought in demolition contractors to remove the slabs that were still up in the air to make it a safe investigation. And we were able to go in after drying it up and do a physical examination of the pier.
The soil beneath the pier foundations had been severely eroded by scour, creating a hole around 3 meters deep, causing the pier to sink down on one end and the bridge above to collapse.
The center pier dropped on the upstream side, and both pieces of the bridge were supported on that pier, and so both spans collapsed into the water because the pier lost support on the upstream side.
Gerard Butch was the project chief tasked with investigating bridge scour across the entire state.
Scour is the most common cause of bridge failure. It's the erosive action of flowing water that removes material from the stream bed. It's a natural phenomenon. So the thinking was that it was sturdy enough to withstand scour.
It was assumed the bridge piers had been protected by the huge rocks or riprap surrounding the base.
The design put riprap, large rocks, around the foundation, and the energy of the water is supposed to be working on those large rocks. And the energy of the water can't get to the foundation because it's trying to shift those large riprap rocks.
But the investigation discovered that most of the riprap was missing.
When we looked at Pier 2, we collected all the riprap from the creek channel and we made a big pile. And we compared it to the quantity of riprap that was shown on the drawings, and the quantity of riprap that we found was 25%.
Without the riprap, these shallow foundations were missing the one thing that was designed to protect them.
So where had all the riprap gone?
The investigation found that riprap placed along the piers had mostly washed away in a massive flood more than 30 years earlier. And despite numerous inspections, it had never been replaced.
When the massive 1987 flood hit, years of scour finally took the bridge down.
Hindsight's a wonderful thing, but not closing that bridge proved to be a tragic mistake.
This was one of the deadliest bridge disasters in US history, and action needed to be taken. Today, Gerard Butch from the US Geological Survey is part of a team monitoring the modern-day threats.
The collapse of the Thruway Bridge resulted in the New York State developing a bridge scour project. The force of water should never be underestimated. The riprap has to be maintained.
High-tech underwater scanners are key to the inspections.
The multi-beam echo sounder is producing a three-dimensional map of the water depth in the channel so we can see where the rocks are, where the scour holes are. This is indicating that the top of the spread footing has been exposed by scour, but it's certainly not in any danger of compromising the bridge.
When you're in a case where you have scour, you need to be maintaining your scour prevention, your riprap, and you need that to be full-time because the creek will flood when the creek wants to flood. It's not going to wait for your next maintenance program.
These readings are revolutionary compared to 1987. Back then, someone would literally have to wade into the water, take a manual depth measurement one dip at a time.
The new bridge, completed in 1988, was built stronger with bigger footings, supported by pilings driven deep into bedrock. And although lessons were learned, the lives that were tragically lost on that day will long be remembered.
It really was a story that touched so many different lives and so many different people in so many different ways. And it's a story that's still being written.
With big construction, how you build is just as important as what you're building. The smallest mistake can have dramatic consequences. Like this catastrophe in Italy that derailed a new bridge.
With this lift, things went spectacularly wrong.
As big engineering went up against gravity and lost.
Once this crane started to go, nothing was going to stop it.
Varese, northern Italy, is nestled into the shadows of the southern Alps. The striking landscape helped earn this town the nickname Garden City. Nicola Antonello is a local journalist.
Varese è chiamata la città giardino per via dei suoi parchi, delle sue ville d'epoca, che sono l'eredità dei signori ricchi milanesi che qui stabilirono la loro dimora estiva. Adesso questi parchi sono a disposizione spesso del pubblico e sono collocati comunque in un'area molto verde con parchi, colline e tantissimo verde.
The landscape in this region is stunning. The lakes and hills have long been a draw for tourists.
But tourists have to share these hilly roads with commuters from both sides of the nearby border with Switzerland.
Every day, thousands of people cross the border here to get to work in Italy or Switzerland. So in 2010, work began on a new rail link that would make the commute both quicker and smoother than by road.
Crossing over the hilly landscape, this was the key to the new line, the Bavera Viaduct. The 438-metre structure consists of 7 bridge spans intended to ease the journey across the valley.
Trains work best on tracks that are straight and level, so they can keep a nice, constant speed between stations. But there are lots of parts of the world, like here in northern Italy, where geography gets in the way, and engineers are forced to build tunnels and bridges.
Although the Swiss section ran on relatively even ground, in Italy engineers faced natural obstacles. Riccardo Assetti is a local engineer.
Questo viadotto ferroviario, che poi vediamo meglio rappresentato nelle fotografie qui sopra esposte, è stato realizzato a una quota ben definita rispetto alla quota del terreno esistente in funzione di quello che era il progetto ferroviario, che non può, proprio per motivi tecnici, avere continui sali, scendi nel suo percorso, ma deve essere il più omogeneo possibile.
As with any bridge, engineers had options when it came to construction.
When constructing a bridge, you can build temporary wooden molds and cast your decks in their final position, or you can make them on the ground and lift them into place using a crane. Each has its own benefits and risks.
In the shallow valley, the bridge ranges from 3 to 18 meters high, which is within easy reach for a crane. So, engineers opted to lift the deck spans from the ground. On May the 9th, 2017, a massive crawler crane was in position, lifting one of the decks, while hundreds of locals looked on.
Engineers have been working on this new line for years, boring tunnels and constructing the new viaduct. Now they were lifting one of the last sections into place. The anticipation was huge.
Sul cantiere c'erano una quarantina di persone, tecnici, operai, ma anche persone che, vista la dimensione del cantiere, della campata e delle gru, si fermavano a filmare e a osservare questo che per loro era uno spettacolo.
But that evening, things took a dramatic turn.
This viaduct had 7 spans. 5 had already been lifted without a hitch, but this time, things went spectacularly wrong.
And it was all captured on film.
Once the crane started to go, nothing was going to stop it.
In 10 secondi si è ribaltato tutto.
Horrified workers and bystanders ran to help. Incredibly, no one had been seriously injured.
Il vero miracolo di questo incidente è che il gruista, cioè l'operatore della gru, è riuscito a salvarsi senza riportare un graffio.
If you look very carefully, just as the crane finally smashes down, the driver comes running from beside the track. This couldn't have been any closer.
The crane and bridge section were destroyed, and local communities were in shock.
Nei giorni successivi moltissime persone sono venute sul luogo dell'incidente per fotografare, fare video e vedere il disastro.
As the dust settled, everyone wanted to know what had gone so wrong. Although the cause hasn't been made public, strong clues were caught on camera.
From the video, you see the back of the crawler start to lift. That's a sure sign that the system is losing balance. And once that happens, there's nothing anyone can do.
Maintaining balance is crucial for any lift, but gravity is powerful and dynamic, constantly working against the crane to bring its load back down to Earth.
The further a crane reaches, the more effort force there is pulling down on the boom. Just like when you lift something with your arm outstretched, it feels heavier than close to your body.
To help balance out those forces, cranes have counterweights known as ballast, but they still have their limits. Push them too far and over you go.
With this crawler crane, the counterweights were attached to the back of the cab and suspended from a rear arm known as the mast. But here, as the load was moved further from the crane, the delicate balance failed. Civil engineer Riccardo Assetti demonstrates.
Tenendo fissa la posizione del contrappeso, può variare la posizione invece del carico che noi andiamo a collocare in quota, per esempio la posa della trave a una certa altezza. Man mano che io sposto il carico che sto collocando in quota rispetto al basamento della gru, rispetto al piano di appoggio della gru, noterò che il contrappeso, pur collocato in maniera idonea, potrà non essere più sufficiente a garantire l'equilibrio del sistema.
With the crane's balance compromised, the ballast on the mast shifted, which spun the crane sideways.
Se giro di 90 gradi lo stesso sistema, spostiamo la distanza, o meglio, facciamo diminuire la distanza tra l'elemento che può stabilizzare e il punto di rotazione stessa, cosa succede? Succede che la gru si ribalta.
Although no one was hurt, local residents were worried the project would be indefinitely suspended. But just 3 months later, a new span was lifted into position with perfect balance, and the viaduct was one step closer to completion.
Every project has dozens, if not hundreds, of risky moments. This is just a reminder that just when it seems everything's going according to plan, something can always go wrong.
The new viaduct opened on December the 22nd, 2017, and trains have safely been using it ever since.
Ai cittadini alla fine con l'inaugurazione hanno vissuto due sentimenti. Da un lato la soddisfazione di un'opera che finalmente rendeva Varese una città più internazionale e dall'altro lato un sollievo perché finalmente dopo 8 anni di cantiere la ferrovia era terminata.
When it comes to big construction, meticulous planning is crucial for every step. Because any mistake at any stage and the results can be devastating. Like this construction disaster in the heart of Boston.
This should have been a routine build, but it went disastrously wrong.
An apartment building collapse on a catastrophic scale.
First the roof, then the next floor, then the floors go one by one and the whole building collapsed.
And a tragedy that shocked an entire city.
People couldn't see anything. People were screaming. I mean, how could a 16-story building just crumble to the ground?
Boston, Massachusetts, founded in 1630. It's one of America's most celebrated cities. Local journalist Fred Tice knows what makes this town tick.
Boston is a special place for one thing because it's such a historical place. This is an old city, several centuries old, and many remnants of that history can still be seen today. It's become a very cosmopolitan city. You really have people coming here from all over the world.
This charismatic city is also a big draw for students. Boston reporter Emily Sweeney is proud of her hometown.
I was born and raised in Boston, and I think it's one of the best cities in the world. It's a big college town, really well known for its education.
Boston has a strong tradition of attracting and producing some of the finest minds in the country, with world-renowned institutions like Harvard and MIT adding to its cutting-edge academic clout.
Boston is perhaps the greatest academic center in the United States, and it's also a really important center for high tech and for biotech.
But with a relatively small footprint for such a major city, Boston's limited space has been stretched thin as it continues to draw in new residents.
There's so many people in the metropolitan area that it's become very densely populated, and if you drive around here, you will notice that the streets are very congested. Boston is the fourth most congested metropolitan area in the United States after New York, Los Angeles, and South Florida.
One solution was to go up rather than out with buildings like this. Containing 17 stories of living space, it towers over its neighbors.
We're in front of 2000 Commonwealth Avenue, and a lot of the residential neighborhoods of Boston, there's a lot of older houses, Victorians, three-deckers. You know, high-rises are kind of few and far between, and this one was one of the few that was, being built at the time.
This building opened in 1984, but it wasn't the first structure on this site. The original tower was a 16-story cast-in-place flat slab construction. 19mm thick precast concrete slabs would sit on columns. Each slab was then held in place by temporary supports known as shoring, while another layer of concrete was poured on top, completing each floor.
Cast-in-place reinforced concrete flat slab construction is popular for multi-storey buildings because essentially there are no beams.
Construction on the original tower began in 1969, and while the current building now houses more than 500 students, its predecessor would never see a single resident. January the 25th, 1971, with construction nearly complete. Around 100 workers were on site when trouble started.
It was a Monday. It was around 3:30 in the afternoon. Suddenly, there was this sound. Workers could hear creaking, moaning, groaning.
The foreman immediately yelled a warning to the workers on the 16th floor of a possible roof collapse.
Minutes later, disaster struck.
Suddenly, the building came crashing down.
The entire east side of the building, 16 stories high, had collapsed all the way down to the basement below.
Some people said it kind of went down like dominoes. One eyewitness said the sound was like 10 jets taking off. Dust filled the air. It was a chaotic scene. Police and first responders were trying to get to the scene, but given it was like in the afternoon, right before rush hour, they couldn't because there was so much traffic.
Of the 100 or so workers on site at the time, most but not all made it out. Around 30 were injured, but tragically 4 lost their lives.
If you see the size of the building and just like where it fell in the middle of a busy urban neighborhood, it's really a miracle that more people weren't hurt or killed.
The tragic and catastrophic destruction shocked the entire city, and Bostonians wanted answers.
Everybody in Boston was wondering, how could this happen? Were there any warning signs? How could a 16-story building just crumble to the ground?
The mayor of Boston appointed a special panel to investigate the cause of the disaster. Based on eyewitness accounts, the structure had started to fail shortly before the fatal collapse. Mehrdad Sassani is a professor of structural engineering.
First, the roof of the building failed. It took some time for the roof to fall on the next floor. And after it fell, the progression was very fast. Floors go one by one, and the whole building would have collapsed.
This progression is characteristic of a type of failure that can threaten concrete slab construction, known as punching shear.
Punching shear failure happens when a slab is either too weak, overloaded, or when any supports or connections below don't have enough strength to hold the slab up.
Punching shear can often cause the rapid collapse of an entire building. But here, after the initial fail, the slab began to sag, buying workers valuable time.
Luckily, the collapse happened relatively slowly, taking more than 10 minutes, so most of the workers had time to escape.
As the roof slab finally collapsed onto the floor below, the sudden impact and extra weight of concrete was too much for the structure to bear, creating a domino effect all the way down to the basement. Punching shear is a well-known phenomenon, so the big question here was not how it failed, but why. The first suspect was the temporary supports or shoring.
At the beginning, concrete does not have the strength to carry its own weight. Therefore, the weight of the concrete needs to be transferred to the slabs below. The shoring would function as that vertical element that support the weight of the newly poured concrete.
It's a crucial stage of construction because the higher the floors, the younger and weaker the concrete is. But here, witnesses reported that there were too few shoring poles to support the slabs.
Not only was there insufficient shoring, but the concrete itself was flawed.
When we look at punching shear failure, there are two important factors that come to play. One is the slab thickness, one is the concrete strength. The concrete was not protected against the cold weather, and as a result, the concrete strength at the time of collapse is estimated to be less than 2/3 of the strength that it should have had.
The investigation found that leaving this fresh concrete exposed to the cold had prevented it from curing or hardening properly.
If freshly poured concrete cools below 0 degrees, the water in the mix can freeze and expand. Potentially, this can damage concrete so much that it becomes useless and has to be replaced.
Here, the average daily temperature was -4 degrees, and the concrete wasn't being protected against the effects of cold weather.
In freezing winters like Boston's, this caused a major problem.
The Mayor's Commission cited a catalogue of errors that contributed to the collapse, but in the end, it concluded that the primary causes were low concrete strength and a lack of shoring. Tragically, in this case, they proved to be fatal.
After the disaster, a large section of the building was left standing, but was structurally unsafe. A year later, it too was brought down.
It wasn't until July 1972 that there was a demolition of the building. A huge crowd gathered, and the skeleton of the building, everything that was left, just came down.
And while it has taken time, the devastating collapse eventually helped lead to a change in protocol.
So the failure of the 2000 Commonwealth Avenue has led to changes in the code to make structures more integrated, as well as the importance of better construction practices in terms of better quality concrete, as well as protecting fresh concrete against cold weather.
It's important for people to remember what happened here and the men who lost their lives here and the lessons that we've learned from it so it never happens again.
When it comes to big engineering, design and construction must go hand in hand. Even the most basic oversight can lead to major catastrophe. Like this construction disaster in Sweden, where devastation struck on a crucial crossing.
It was shocking. All that concrete absolutely collapsed. This was a major accident.
A bridge catastrophe that caught everyone by surprise.
I had never seen an accident like that before. You don't know who's under there. It was just a disaster here.
And a sudden collapse with workers still on top.
One man, he was covered in concrete from bottom to top. Concrete is like mud, it sucks you in.
Around 200 kilometers northwest of Sweden's capital Stockholm lies the small town of Ludvika. Although its modern-day population is just under 15,000, it was once a powerhouse at the heart of Sweden's lucrative copper mining industry.
One mine, about an hour from Ludvika, was once the largest copper mine in Europe. As an added benefit, the leftover rock could be turned into a hard-wearing, bright red paint, which has become famous across Scandinavia.
With the mines came the railroad to move this valuable metal out for production, a vital means of transportation that Ludvika still relies on. Anders Hansson is a TV reporter.
It's vital for this region that the train keeps running. A lot of people commute from other cities, and we have to ship out a lot of industrial goods.
Running right through town, the railroad separates the community from Ludvika's main source of recreation, Lake Väsman, making this bridge one of the busiest thoroughfares in town.
There's the town on one side and there's the lake on the other. The lakeside is very popular. The bridge is the only place where you could cross the railway.
The first bridge built here in 1905 was a single-lane steel crossing that was struggling to cope with the demands of modern traffic.
The old bridge was a quite narrow steel bridge. One lane, so 2 cars couldn't meet on the bridge. Tricky for the community to reach the lake. So they demanded a new bridge to be built.
The old bridge was very bad. It didn't do its job. People had to wait for other cars since they could not pass on the bridge. A new bridge was badly needed.
In 2017, construction began on a bigger, better crossing. But with a busy rail line running directly below the worksite, the team needed a strategy to build without halting train traffic.
To minimize disruption, the bridge will be built using a technique known as cast in situ.
Wooden moulds, known as formwork, built in the shape of the bridge, raised up and supported on top of temporary steel supports.
The concrete is then poured into the mold, and when hardened, the deck is simply lowered into place.
This is a tried and true technique, allowing entire bridges to be built while traffic continues to flow below. Thursday, July the 13th, 2017, shortly after 2 p.m. As engineer Jens Skans explains, construction of the new bridge was well underway.
They had poured about 2/3 of the concrete in the wood frame, and the midsection was taking its full load.
Around 15 workers and 700 tons of concrete were overhead, when suddenly, the entire section came crashing down.
First there was a large bang, followed by a snapping, popping sound. A few seconds later, the wood frames started to crack, crumble, and the bridge collapsed quite fast.
As reports of a disaster began filtering in, local journalist Lotta Ullin received a call from her producer to get the news on air fast.
As a reporter, I'm used to report from accidents, but I had never seen an accident like this.
The wooden formwork, steel, and tons of wet concrete had fallen onto the active train track below, taking the workers on the bridge down with it.
It was just a disaster here. A lot of people around the place that are wondering what has happened. It's quite scary because you don't know who is under there. We didn't know if there were people that was hurt.
Reporter Anders Hansson also witnessed the devastation firsthand.
This was a major accident. It was shocking to see all that concrete that had absolutely collapsed. From the looks of it, I was expecting casualties.
Especially since one worker was thrown headfirst into the wet concrete.
He was covered in concrete from bottom to top.
The rest of the team there were trying to pull him up because he couldn't get up.
He was submerged, head down in the concrete, and it's so thick that you can hardly move in it because concrete is like mud, it sucks you in. Scary.
Thankfully, the worker survived. And while 11 more were injured, 6 of them seriously. Despite the devastation, there were no fatalities.
This thing was so big, you wouldn't believe. It's only when you stand there and look upon it that you realize how big a bridge of this kind really is.
Tragedy had been narrowly avoided, but with the railroad in chaos, people wanted answers. Engineer Jens Skantz from the Swedish Work Environment Authority was part of the investigation, which began by examining the steel in the incomplete bridge structure.
We found a lot of snapped metal pieces. We found a lot of bent steel beams. Not a single piece that was straight anymore. It was all bended or broken in some way. We checked it to the drawings, and our opinion is that at least the framework and the steel and so on, it matched. It matched the drawing.
The structure seemed to be built according to the designs, so in theory, the falsework should have been able to carry the weight of the concrete. But in reality, things didn't go to plan. The obvious question was, why?
Attention turned to the wooden mold where the concrete was being poured.
The wooden formwork was harder to inspect because it was cracked, crumbled, and we checked what we could check, and we didn't find anything that caught our attention.
With the cause of the disaster still a mystery, investigators shifted focus to the steel falsework. They found one key component had been overlooked in the original plans.
Normally, when you build a scaffold, you have to make sure that the load is spread evenly. And to do that, you have to have a lot of diagonals, creating a pattern of loads taking the weight down to the ground. And one of the reports point that there are too few diagonals supporting in this steel frame.
A miscalculation meant bracing was missing, crucial for resisting any lateral or horizontal movement when concrete is being poured.
When you're pouring tons of heavy, wet concrete, one thing you're going to get is movement. So if that isn't properly braced, any lateral movement could bring the whole thing crashing down.
The weight and motion of the wet concrete overwhelmed the temporary structure, causing the catastrophic failure.
At the end, they found that the bracing that was supposed to hold up the mold was too weak. They had been working so hard in order to try to make the trains run all the time. This was really bad.
With a vital connection severed for both commuters and commerce, a fix was needed fast.
Since the railroad is so important for this area, they wanted to open the tracks again as quickly as possible. So they had to work very hard for a couple of weeks in order to clear the tracks again and get the trains running.
Once the debris was cleared, the bridge was rebuilt. This time, both the wood and steel were up to the job. And not only are the trains rolling once more, but Ludvika's citizens can now easily access the natural beauty of Lake Väsmön just across the tracks.